An important instrument to understand the distributed ecosystem is its reference architecture, which is in effect a map of its components and how they work together. We will learn here about reference architectures by example, one by one. Together with a large community of experts, we defined serverless computing as a modern cloud computing paradigm encompassing a class of cloud computing platforms that allow one to develop, deploy, and run applications or components thereof in the cloud without allocating and managing virtualized servers and resources, and without being concerned about their other operational aspects. There are many serverless applications already in operation. Together with a group of experts, we analyze these applications as they appear in peer-reviewed publications and in open-source projects published on GitHub. We can run this software. In this example application, a social media user wants to publish a status update, which should be seen by all of this user's friends. This happens every year more than 1 billion times per day on many different social media platforms, such as Facebook, Twitter, and Instagram. We found many more types of applications that leverage serverless computing for core functionality, for utility, and for scientific workload execution. We also found why these applications are developed to leverage serverless computing, to save costs, for built-in scalability, and simply to automate operations. The reference architecture for the serverless social media application we introduced earlier. With serverless technology, the cloud provider abstracts away the server management, provisioning servers with fine granularity, on demand, and with a pay-per-use model. To benefit from this, the serverless software gets transformed. Simplified, the process of posting updates proceeds as follows. First, the user posts a status update using their mobile clients as an HTTP request sent to the API gateway, which operates as serverless request routing. That is, a specialized function that routes only needed requests and runs very efficiently without further developer intervention, fully automated. The next step proceeds. The API gateway triggers a Lambda function, the serverless name for a compute task, which queries the user's friends from a DynamoDB table, which is serverless storage, and then publishes the status update to friends using the simple notification service, the SNS, which is a serverless publish-subscribe service. Finally, SNS generates push notifications with the status update for the user's friends. Tens of other serverless functions also get invoked to authenticate the user, authorize posting messages, copy data between various locations, and on and on. All of these are orchestrated by resources managed by the cloud operator. In the reference architecture illustrated here, this complex ecosystem is depicted with just a few boxes. With it, we see three main layers. The workflow composition layer, which orchestrates the application workflow. The function management layer, which coordinates the execution of a single function. And the resource orchestration layer, which manages the resources needed for the entire application. For a different direction, graph processing is an emerging workload that has already reached a high degree of importance for society and business. Graphs are universal data abstractions able to encode any entities and their relationships. There is ample mathematical apparatus to support graph operations, and network theory has made robust advances for over 150 years. Today, the largest graphs are truly large-scale, exceeding by far the ability of any common machine to process them. Enter distributed systems, which can combine many different machines for the task of graph processing. Together with a large community of experts from all around the world, we propose the reference architecture for graph processing illustrated here. The architecture includes the following layers. Layer 1, the infrastructure layer, provides physical and virtual resources to be used by any application. Layer 2, the operating services layer, provides services across resources, including data streaming and synchronization, key concerns you've encountered in this course. Resource managers in Layer 3 provide static and dynamic resource management and scheduling across all the resources. The backend and the front-end layers, layers 4 and 5 respectively, represent specialization efforts. Conversely, layers 2 and 3 may generalize techniques initially developed in layers 4 and 5. You've seen this large ecosystem earlier in this module. This particular distributed ecosystem is important for a particular science, astrophysics, but it turns out there are more distributed ecosystems built for science, engineering, and many other fields that equally require massive computation. How are these built? First, the data centers in this ecosystem can be mapped to the reference architecture as we did for graph processing. You can see more components representing a larger workflow and the emergence of a market of data and algorithms, but by and by, in the same architecture that you saw earlier, you can put this application. And what about the geo-distributed operation? We move a level up in the abstraction to a reference architecture that covers cloud infrastructure, including large data centers, also edge infrastructure, including small data centers, and finally endpoints, the smallest infrastructure. Overall, the reference architecture simplifies in detail, but we can get into more detail from this level, and if we pick the cloud component, we will get to the reference architecture for data centers we explored earlier. Any component in that reference architecture can be further explored in more depth. We have just introduced a method to use reference architectures to represent any level of abstraction necessary to understand the problem at just the right level of detail. Various computing paradigms combine various subsets of these resources. These paradigms are mentioned in the arrows below the reference architecture. Thus, from this reference architecture, one can construct subsets, which is a method to get different paradigms to discuss with each other effectively around an all-encompassing reference architecture.